Now that we've discussed the rules and the procedures for actually finding derivatives of the various types of functions that we know, we turn our attention to a new notion which is called implicit differentiation. Now, first off, differentiation is this wonderfully long word. Originally, this work was all done in Latin. That's why there are so many syllables for everything. Differentiation, differentiability. Later on, we're going to have anti-differentiation, and all. The number of syllables goes crazy, but that's primarily because this work was originally done in Latin. But anyway, differentiation means the process of finding the derivative or computing the derivative. And there's this notion of called implicit differentiation. So to sort of understand what's happening here, let's take a look at the expression x times y equals 1. Now that's an equation, and this is called an implicit relationship. Now in this particular case, it is possible to solve this for y. So the question is, what is... And now we're going to need to shift in our usage of notation, because it doesn't really make sense to say, what is f prime of x? Because there is no function here. And so this notation sort of begins to lose its effectiveness. And so when we discuss the notion of implicit differentiation, we do not use this notation. We could, rather than use f prime of x, we could use y prime. However, for some other technical reasons and for some other concerns that occur, particularly when we take things like courses like differential equations, this is not as helpful, it's not as particularly useful as a different form we're going to use. When we discuss the notion of implicit differentiation, we use the symbol typically dy dx. dy dx. Now we usually simply say dy dx. dy dx. What we strictly speaking mean is this, and the official way to read this is the derivative of y with respect to x. And so you'll hear this phrase, with respect to x, with respect to x, the derivative of y with respect to x. When we write this, there actually is information contained in just the writing itself. Here's what this means. Think way back to the very first time you first talked about functions, and probably somewhere back in your algebra course, you had some sort of I always call these little amoeba-like pictures. Here's the domain, here's the range, here's some function, and we had, typically you would have had things like 4 and 2 and 5, and over here you would have numbers like, you would say something like, let's say 16, and this might go to 4, and this might go to 25, or whatever function you were playing with. And then you had an x value here and a y value here. Now the way we would have done this, is pretty clear. Suppose we're working with the square function. Well, when you work with the square function, again, think back to the very first time you played with the square function. You didn't know what the picture looked like. So what did you do? You wanted to draw the graph of the square function. What did you do? You made a little grid. Do you remember this? You made a little grid, and what did you or your instructor do? You randomly selected values to put in the x column. The number you select depends upon what your instructor required of you, usually 3 or 4 or 5 or 6 or however many. But we choose some values, so you choose. Here's the key, you are free to choose whichever x value you want. I can choose x to be 6, but I'm not free to choose y. As soon as I choose 6, if I choose 6 in this set, 6 corresponds to a specific number. This number is not freely chosen, it is forced. This is 36 in this instance. And so we compute, right? 6 squared is 36. I'm free to choose -3, but once I freely choose this, This value is not freely chosen. This value, here's the phrase, the 9 depends upon this value. The 36 depends upon the 6. The 6 doesn't depend on anything. And the language we use is the values in this column, the values in this set, the values in the domain, those are independent. In fact, in this scenario, we say x is the independent variable. And in this scenario, y is the dependent variable, because it depends upon the choice. Values in this set are dependent. The range depends upon the choice of the domain value. And so when you write dy dx, you are tacitly saying, in this writing, without saying it, you're actually expressing the notion that dy dx, this is the dependent variable, this is the independent variable. I need to spell it correctly. Dy dx is the independent variable. Now, we'll say this. If you hang around the coursework long enough, you're going to get into Calculus 3, and you'll do things like this. dz dt. Which variable is independent? T is independent. Which variable is independent? Independent. Z is dependent. T is the independent variable because that's the value in this denominator. When we say, when we say with respect to x, that is mathematics code for x is the independent variable. This is the derivative of z with respect to t. So this is the derivative of z, and you'll see this over and over and over again. Anyone who knows what you're talking about has done this before. How many times this gets abbreviated when we took graduate school mathematics, with respect to t, derivative of z with respect to t. When we say with respect to, we're saying that is the independent variable. And there's nothing magic about z or t or x or y. In fact, it is possible to find dx, dy. It doesn't happen very often, but we will see some problems potentially where we will have dx, dy. And in this case, y is the independent variable and x is the dependent variable. It's not this setup, but that is possible to be done. And so, all that to say this, our notation we're going to be using is, we still want the derivative, perhaps we want the derivative of y with respect to x. We want to find dy dx. Y is the dependent variable, x is the independent variable. All right? That's what we want to find. So let's make a note of that. We want it corresponds to, it is not the same thing as, that corresponds to finding the derivative of x if this were an ordinary function. All right? So, one thing we could do is this. In this particular case, because this is not particularly complicated, one thing we could do is solve for the dependent variable. In this case, we actually could solve for the dependent, now, which is the dependent variable. Dependence in the numerator. It's opposite. Dependence in the numerator, independence in the denominator. All right? With respect to is the independent variable. dy with respect to x. X is the independent variable. Y is dependent. We could solve for, in this case, solve for y. In which case, that would look like y is equal to 1 over x. And now, we could, if we wanted to, write that as y equals x to the negative 1. And then we could find the derivative of y with respect to x is equal to negative 1 times x to the negative 2, right? It's just the power rule. But then we could rewrite that as negative 1 over x squared. That is certainly allowed. That is more than fine in this particular case. The problem comes in this way. Sometimes solving for y is either not very easy, extremely difficult, sometimes not even tenable, not even possible using elementary means. And so this could be much more complicated. It could be things like this. We could have x to the 7th minus 3y to the 3rd plus x squared is equal to y to the 4th minus 1 over x. I mean, we could have some bizarre equation, and solving for x or solving for y might be very, very difficult, maybe not even possible. We could have something like this. xy plus tangent of y is equal to x. Solving this for y is going to be just a nightmare, even if it's possible. Same thing here. And so sometimes it's not possible or much too trouble to go to. In those kinds of settings, in particular, if the relationship is expressed in form of an equation rather than expressed in the form of a function. Roughly speaking, when the relationship is expressed in terms of an equation, we typically call this an implicit. This is an implicit relationship between the variables. When you represent it as a function, then this is an explicit. And so what we have been doing so far, we have had y equals function of x. And so that has been y explicitly expressed in terms of x. But what we're going to now consider is, what if they're expressed in terms of equations? What if it's this, even a simple equation, or a much more complicated equation, or a very untenable equation? So that's our process to look through. All right? And so we will go through this notion of talking about how to do these computations using implicit differentiation rather than trying to solve for the variable and use explicit differentiation. So what we'll do with the next video is, okay, now that we have this terminology and sort of understanding what's happening, now we're going to go to the actual computation, and that's going to be up next.